In this video, we're going to be discussing nervous tissue physiology. As we do this, at the bottom of the slide, we've got a micrograph of a neuron, just so we can refer to it as we need to. This is the axon of a neuron, and it would help if I had my pen on as I was trying to do that, so let me turn that on. So this is the axon of an unmyelinated neuron. We're going to draw the membrane of that. So the membrane is going to have various proteins scattered throughout it. The proteins are going to be ion channels. The ion channels can be either ligand or chemically gated, or they can be mechanically gated, or they can be voltage gated channels. When we say that they're gated, that means that they can be opened or closed. When we preface that with either ligand, mechanically, or voltage gated, that tells us what will open or close the gate. If it's ligand or chemically gated, that means a chemical has to bind to the gate in order to open the gate. If it's voltage gated, that means we have to change the voltage across the membrane in order to open the gate. If it's mechanically gated, that means some sort of mechanical force, like a stretch or a touch, has to act across that membrane in order for us to open that gate. A lot of times, chemicals or mechanical forces are what are going to start an action potential, while a voltage gate is what's going to propagate or allow that action potential to continue to move in a forward direction down that axon or dendrite if we happen to be on the dendritic side of a neuron. Okay, so I'm going to sort of get us started at the beginning. Let's say that we're on the dendrite side. We're trying to receive information from another neuron. Let's say that another neuron is releasing a neurotransmitter. That would mean that we need a receptor on the dendrite of our postsynaptic neuron. That receptor is going to be a ligand-gated receptor. So when the neurotransmitter binds to the ligand-gated receptor or the ligand-gated channel, what's going to happen is that channel is going to open, and if the whole purpose of this was for us to try to stimulate the postsynaptic neuron, then sodium is going to flow in through that channel and then flood in to the inside of the axon. And remember, sodium is a positively charged ion. So what that does is it's going to bring its positive charge to the inside of the membrane. Now, when we started, because of sodium-potassium pumps and leakage channels, the membrane had been positive to the outside, negative to the inside. But because of this ligand channel, we have flipped the charge. That's called depolarization, and depolarization is the basis for an action potential. So by virtue of us opening that ligand-gated channel, we have started some sort of a potential on this membrane. Now, depending on if we're on the dendrite side or the axon side, we can either be starting a graded potential or we could be starting an action potential. The difference between those two things is that graded potentials get weaker the farther away they travel from where we start them, while an action potential, once you start them, they're going to continue all the way to the end at the same intensity the whole time that they travel. So since I was saying we were trying to stimulate one postsynaptic neuron from another neuron, I was saying that we were going to be trying to talk to the dendrite, which means we just started a graded potential. Well, one signal from one neurotransmitter depolarizing this one place would not be enough for us to continue this signal all the way down this axon, or this, I should say, membrane. And so that graded potential would eventually weaken out and it would stop. Okay, here's where I'm going to stop with that particular ink color and erase all that ink, and then we're going to do a different scenario in a different color. This time, I'm going to say that we're working on the axon side. A potential had been traveling, a graded potential that was strong enough that it reached the axon hillock on the other side of the cell body. That hit a voltage-gated channel that was on this axon side off over here. What that meant is, because that potential hit this side and it flipped the charge over here so that we became positive to the inside, that flipping of the charge automatically opens this gate and it allows more positive sodium ions to flood in this spot, bringing their positive charge in, flipping here. There's going to be another sodium gate beside that, which is going to open. More sodium is going to flood in, which is going to allow us to flip the charge there, which is going to allow yet another sodium gate to open, and we're just going to keep doing that. This is called propagation. Propagation happens because one sodium gate allows the next sodium gate to open, which allows the next sodium gate to open. And this is why action potentials are what your book calls all or nothing. They happen or they don't. They don't get weaker over time. And that's because one door allows the next door to open, which allows the next door to open. Graded potentials on the dendrite side, they don't work like that because these doors are spaced so far apart that opening one door doesn't automatically make the next one open. We have to hit a door on the dendrite side with enough force or hit it sequentially so many times in a row that it allows us to flip the charge enough that it would make a door farther down the membrane actually open. And so it's harder for a graded potential to actually turn into an action potential, essentially. Hopefully that helps you understand the difference a little bit better between a graded potential and then an action potential, and how dendrites are different than axons on a neuron.